So today we're back on track with waves and sound. We're doing sound today. And so we're in section 17.1 through 17.3 and 17.6 through 17.7. Probably I'm going to split this one up over 2 days, actually. In part because I want to do a few demos with it, and in part because I want to do some examples and the like. And it will not all fit within one class period. So today I have a few assorted demos, if everything will cooperate. Okay. First one, we need to go onto the internet, so that's always risky, around here anyway. Let's see if we have it. Yeah, this one will work. Okay, so this one lets me play a sound wave. I can make it a sine wave, a square wave, a sawtooth, or a triangle. And I can change the frequency, and I can change the amplitude. Alright, so this one is the generic settings. If I hit play, it should be at 440 hertz. Change the frequency, say if it will cooperate with me. Here's 200 hertz. Okay. So you hear the difference, obviously, not just in volume. Turn the amplitude down. Volume and amplitude go hand in hand. If I move this back to 400, you get a different pitch. Okay, so frequency seems to be related to the pitch and sort of tone of the sound. There's a little more to it, of course, because I can keep a given frequency and switch the shape of the wave. So this is a sine wave. Here it is as a square wave. Here it is as a triangle wave. Here it is as a sawtooth. Okay, so those are all the same frequency, but slightly different sounds to them. As an aside, that shape that the wave is making determines why you get a different sound playing the same note with different instruments, as it turns out. It turns out, and this is one of the things that I saw somebody studied at this conference I went to. It turns out that they took a concert clarinet, and then they took a concert, like an opera singer, and had both do the same note, like an F sharp or whatever. And they looked at what the signal of the two of these things are. What does the wave look like? Frequency's the same, volume's the same, but slightly different shapes and slightly different mix of overtone frequencies to them. It turns out that there's what's called overtones, you saw this a little in the lab, or it was hinted at in the lab, which is when you did your open tube sound experiment this last week, you found that you had some particular frequency that was resonant with the tube, and so you changed the tube length to get it resonant with the frequency of the fork you had. If you used many different forks, or if you could change the frequency of the fork, and you're going to do this week, actually, but with a string, what you'll find is that there's multiple frequencies that are resonant for a given length. So you have a fundamental frequency, it's the smallest frequency that's resonant, the longest wavelength that's resonant, and then you have a bunch of overtones, which are usually integer multiples of that frequency, 2 times as much, 3 times as much, etc. So the mix of overtones is a little bit different for different instruments. And then you may wonder a little bit too about what's the difference between a reasonably competent singer, somebody who's like an undergraduate, but maybe they're far along in undergrad, they've had some voice lessons and so on, or they've had some clarinet lessons or whatever, and a professional quality. And the answer is that the professionals somehow have less overtone when they play whatever note they're playing. This was what they found in this study. So those overtones basically can add to the main wave to change the shape of the wave. So if you have only one frequency, you get what's called a sine wave, what we've been seeing. If you have many frequencies, the sine waves add up together to make something different. For example, if you have 2 frequencies, you get what's called a beat. So let's open a second one of these. What we're going to do is, actually, I kind of want the default volume for both, so that they're the same volume. So I guess I'm opening a third. Let's put one of these at 400 hertz. We'll put the other one at 402 hertz. Okay, apparently we're going to do 392 hertz. There. Alright, so there's 402 hertz. If I also play the 400 hertz, listen to what happens. So what has happened when I played both of those? On the one hand, you maybe heard the frequency change just a little bit, but maybe you noticed that, maybe you didn't. It actually changes it so that the main, what we call the carrier wave, will sound like the average between those 2 frequencies, 401 hertz. But at the same time, you heard that kind of, that kind of thing. That's what's called beating. So these 2 waves beat together, and what that basically does is it makes it so that the volume of the wave increases and decreases with time. In fact, the rate of that beating is the difference in the 2 frequencies. So at 402 hertz and 400 hertz, the beating pattern should be twice a second, 2 hertz, 402 minus 400. Now, I want to change it again. Let's make this one 398. Somehow. We're going to play them again. You'll notice that the beating happens more quickly than before. So our beating is happening more frequently. It's now 4 times a second rather than 2. And I'm going to change change it, and then I'm going to replay it again. This time I'm going to make this one 404 hertz. I'm going to make this one 396 hertz. That means the carrier frequency should be the same because the average of the two is still 400. But now we're going to have a different beat frequency. Ready? Okay. So slight difference. Okay. So that's item one. That's demonstration number one of sound waves. They can beat together somehow. The math to it is outlined in your book, although I'm not going to go too much into those details. There's essentially, you add two sine waves together. You can do it mathematically. What you'll find is that you get a cosine wave that has an omega t in it. You'll get a sine wave that has a second omega times t. The first omega, it turns out, is the average of the two frequencies. The second omega is the difference of the two frequencies. Okay. All right, so is it actually a wave? This is one question we might ask of it. I'm going to actually turn the frequency down again, so we can hear what does 100 hertz sound like. There's 100 hertz. It's a nice bass. What I'm going to do now is I'm going to open up this guy because there's a built-in microphone. And we're going to see if we can detect the wave with the microphone on here and display it on this and see what it looks like. All right. Record. So this doesn't necessarily look like a sine wave here, right? But if I zoom in on it, if I zoom in horizontally, you see that it is in fact a sine wave. All right, and we can count, let's say from this point to this point, this is 1/10 of a second. We could count how many oscillations does it go through. And what we'll see is it went through 10 oscillations in that 10th second. All right. So maybe we can count troughs. So first trough, so here's one oscillation, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So in 0.1 second, we had 10 oscillations. Frequency, therefore, should look like n over delta t. It matches the 100 hertz that we just explained. All right, so sound is a wave here, a waveform of some sort. This sound wave, the sine wave, put out a sine wave here. We can do that also with a function generating speaker, but it's more convenient to do online. What else can we figure out about these sound waves? Well, I guess one thing we could do is come back here and do this thing again. All right, so let's make this, whatever, 401. We'll make this 399. All right, so when you add the two together, what is the beat frequency that we should get? Two. All right, so beat frequency oftentimes for beat frequency, we'll use a capital omega. Should be frequency 1 minus frequency 2. So 401 hertz minus 399 hertz is 2 hertz. The carrier frequency is the average of the two. Average of these two should give me 400. All right, so we come back over here. Oh, one little problem is that I need to do this really nicely. I'd like to have them have the same volume. So hence I'm reopening it here. We play the 399. Play the 401. We open this guy up, we reset it. We'll go ahead and play it, and then we can. Learned maybe a few things from this, just from what I did here, right? One is that I started by holding it up over here somewhere, and we got this part of the pattern. In fact, it's so intense that the detector cannot detect the maximum and minimum volume to it. It's too loud. So I tried to adjust the position, still a bit intense. So then I moved my hand over here to try and turn the volume down, and that's when we started getting this pattern. Okay, so one implication is distance from the source affects the intensity detected by the detector. Okay, we'll come back to that point in a moment. Let's look at this part of the graph, which is the part that we can actually see the whole wave. So you see that it makes like this solid wave looking thing. If we count time between these, we see this is 21.6, 21.8, 22.0. This is presumably 21.5. So that's about a half a second from here to here. And then here's 22.6. So this is 1 whole second. Okay, implication, the beats are in fact 2 hertz. We're getting 2 per second. Now let's zoom in a bit on the wave, because again, if we zoom in enough, we might see an actual sine wave within that. So this is your carrier frequency right here. All right, so for this one, you'd have to pick and count over some set amount of time. So this is 21.73, this is 21.76. So delta T, 21.73 to 21.76, that's 0.03 seconds, right? And this may be an awkward number to do. Let's do from 21.72, in fact, so we'll get a nice even 0.04. We don't end up with a repeating decimal if we're off. All right, so we're at a peak here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we have 16 in this span of time. So again, we do our calculation. Frequency, this is the carrier wave that we're specifically looking at. So this is our carrier frequency. This should look like our number divided by our time. So 16 divided by 0.04 seconds. All right, we can move the decimal over 2. We can move the decimal over 2. This is a 1600 over a 4. 400 hertz. Matches our prediction. Okay. All right, so this thing I showed you a moment ago gives me different volumes depending upon how far away from the source we are. But this isn't a very good way to maybe measure the volume because we're using some arbitrary units. It says it's an intensity, and then it just essentially says we're not giving you units, just normalized units of some sort. So what is an intensity? What does this term intensity mean? All right. That's a new term that we haven't really encountered. I think maybe you saw it kind of sort of one time in one homework problem in Physics 1, and all the terms in it were defined for you. All right, so our new term, intensity. The intensity is defined as the power per unit area. Some sources use an A for the area here, some use an S for the area here. And in fact, I'm going to put an S. The reason for my wanting to put an S here is because it turns out that intensity is related to the amplitude of the wave. You see why we wouldn't want to have an area here? Intensity is related to the amplitude of the wave. Now we have two things that start with an A. Okay, so amplitude, we're using area, S. Amplitude, we'll use a sine max. Why sine max? Because when I introduced waves, I showed you the arbitrary equation for a wave could be psi equals sine max times the sine of something. Psi is just now your arbitrary term for what is creating the wave. What creates a sound wave, by the way? What is the amplitude in? What is oscillating? Does anybody remember? No? No one remembers? Yes?
The vibration of an atom.
Okay, so it's vibrations of atoms within the air. The sound waves you guys are all hearing are waves being carried by air. So what might we say would be oscillating? Okay, you have atoms that are being displaced from equilibrium, so that's one option. That's not very easy to measure though, is it? So what else could we say was changing? Something that's maybe a little easier to actually measure. Ideas? Pressure. Pressure is oscillating. Okay, hence why I want to use the arbitrary one, because what would we use to represent a pressure? P. But we're already needing P to be power here, so let's use the arbitrary symbol. And bear in mind that this is pressure wave. This intensity term, by the way, it's valid not just for sound. It's valid for electromagnetic waves. You could define some version of it for a wave on a string, etc. So we actually do want to leave it as power per unit area, and we do want to have a generic term here. It could be the electric field, as we'll see later in the semester. All right, so power per unit area. That gives us the intensity. The intensity combined actually with the frequency determines how loud it is. If you don't believe me about that, one more demo. This one's a simple one. Let's go back to our online tone generators. Stop these two. Play around with this one. All right. So nothing's on right now. Let's put this down. I'm going to set the volume. I'm going to put it sort of here in the middle somewhere. I'm going to turn it down on this speaker so I don't blow my speaker out. I'm going to start somewhere with a low frequency. All right? Maybe 100 hertz. Okay. Let's make the frequency higher. Let's make it 500 hertz. This is a sawtooth wave. I want a sine wave. All right, so that was 100 hertz. Here it is with a sine wave. Now let's listen to 500 hertz, same sine wave. I've done nothing to the volume. Ready? You can hear that a lot easier, right? That's a lot louder. If I change it again to something else, maybe 5,000 hertz, also sounds like it's at a slightly different volume. Okay. So it turns out that how loud the sound is a combination of the intensity, and hence the amplitude, and what frequency that's at. Loudness is a physiological response. It has to do with how your ear detects it. You have in your notes and in your book a chart that you'll need to use on the homework. It turns out that loudness is measured in a unit called fons. We'll come back to this idea later because a lot of what I'm going to do next time is look at your hearing range, how well you can hear stuff. We can test what frequencies you guys can hear for the fun of it, how loud stuff sounds, and also ultrasonic sound and some applications. So this time, we'll set this idea aside. We'll come up with the next nearest thing. Okay, the next nearest thing to loudness is intensity. Now, before I told you that we measured loudness in fons, if I was going to ask you, how do you measure how noisy a room is, what unit would you have said? Without knowing anything about loudness and it being in fons, what unit do you usually measure noise in? Yes?
I would always say hertz.
Hertz? Okay, so that's a frequency. What's that? Decibel. Yeah, decibel. Everybody agree with decibel? You want to know how noisy a room is, you measure how many decibels. All right. So looking back at this, the intensity here, this is a power per unit area. What's the unit of a power? That's joules, that's energy per unit time. That's joules per second, that's watts. Area is in meters squared. So on the one hand, we have this thing called a decibel, and on the other hand, we have this thing called watts per square meter. Are the two things the same? Is a decibel just another word for a watt per square meter? In which case, why would we use decibels? Any thoughts? So it turns out that they are not the same unit at all. In fact, decibels don't even have to measure sound. They can be used arbitrarily to measure whatever you would like. They are usually used in measuring an intensity level. It's called intensity level, not intensity. But you could use them to measure other stuff as well. It turns out that the decibel is a convenient way to represent a large range of numbers that you may detect. Okay? So why would we detect a large range of numbers? Does anybody know what a rough scale of the range of sound levels that you might find in a room or in a conversation or whatever? Daily life, let's say. Does anybody know what a rough range would be in intensity scales, let's say? Turns out that an approximate range, if you can go someplace that's very quiet, and you can get down to what would be roughly 0 decibels, it's very hard to do that, obviously, then you're looking at an intensity level, 0 decibels, you're looking at an intensity of about 10 to the minus 12 watts per square meter. Okay, maybe on that same day, you and your friends got tickets to a concert. So you go to the concert. You got good tickets, so you're up near the front where the big speakers and the band and all that are. Now, you're looking at something like 100. The sound goes up quite a bit. You can get 120 decibels from some of the areas. And you're back a ways from it. As we just saw with the detector, the distance here matters. What would you expect the relationship between distance and intensity to be, for what it's worth? How would you expect the intensity to vary with the distance from the source? Yes? Okay, so as the distance gets greater from the source, the intensity goes down. That should make some intuitive sense, right? I have to talk a little bit louder than my normal conversational voice when I'm teaching this class because some of you are at the back of the room and I don't normally hold one-on-one conversations for an extended period with somebody at the back of the room. Usually it's a little bit closer up to the front. So my normal conversation voice is about this loud. Okay? So, you know something about you have to talk louder if you're talking to somebody who's farther away. If I had to teach this in a large auditorium, I would probably use a microphone, but if not, I'd have to practically shout to be heard in the back. So we know that it's going to be that the farther away you are from the source, the lower the intensity should be for a common source between two observers. Can we say something about the actual relationship between the distance to the source and the intensity that's heard by two observers? And the answer is yes, we can if we know something about the source. So for example, what we need to know is how the source emits sound waves. How are the sound waves propagated? For the simplest type of source, you have a point source. This would be something akin to, like, you have those little poppers, you throw them on the ground, they sort of explode and make a little bang sound. Imagine tossing one of those into the air and having it explode in the air, like a small firework that you throw in the air and it explodes in the air. It's not exactly a point source, but it's a very small source. The sound wave is being emitted from a very small area. We might approximate it as a point source. And now if you've done this in the air, every direction looks the same to the sound wave. Sound wave will propagate uniformly from that in the shape of a sphere. You can think of the wavefront as taking a spherical shape until it encounters some boundary. Alright, so a point source propagates like a sphere. Something like our speakers or somebody talking is not exactly a point source. In fact, there's some directional preference. The speaker, for example, is louder right in front of it than it is right behind it for most speakers. Same with somebody actually talking. If somebody was standing behind me, they would not hear me as well as you all can hear me because I'm facing you. If I turned around and gave the whole lecture talking to the board, you get some echo off of this, you get some from behind me, it wouldn't be as fun. Or maybe it would, I don't know. Alright, but we can maybe approximate something like a speaker or a person talking as if maybe the sound expands more like a hemisphere than a sphere. It doesn't really change the argument that I'm about to make here. I will do it for the point source. For the point source, you have a sound wave that's emitted here. Sound wave's emitted. This means that energy has been expelled to create this sound wave. It's been expelled in some amount of time that determines the extent of your sound wave, for example. All right? So now I want to know what the intensity is. How do I find that? Well, I got to figure out how much of an area this sound wave is sort of covering. What's the extent of the sound wave area-wise? And the answer to that is, well, how far away are you when you're trying to detect the sound wave? Because if I'm right here trying to detect the sound wave, I have a sphere that has this size out of the board. All right, so this would be the radius r. The area S would be 4 pi r squared. If I'm out here, I'd have a different value for r, and therefore a different value for the area. Okay, implication of this is that for a point source, I'll write it over here, I for a point source should look like the power divided by 4 pi r squared. Now the power within this wave remains constant as long as the wave is not being absorbed by something. Right? And attenuation is kind of rough to deal with, so we're not going to deal with it in this class. It does get absorbed a little bit. It's absorbed a lot if you have like a room like this where there's a lot of people. If you're outside and it's really snowy that day, the snowflakes will absorb it, water droplets, that kind of thing. All those can help add to attenuation. We're going to ignore those effects. This right here says if I want to compare the intensity at two distances from the source, I1 divided by I2, I'd have to divide these things. I'd have P1 over 4 pi R1 squared divided by P2 over 4 pi R2 squared. All right, well, the power I just said is the same. That's also known as energy conservation, as long as it's not being absorbed, attenuated, reflected, anything like that. And I can cancel out the 4 pi's from both because that just is a constant. What I'm left with is R2 divided by R1 quantity squared. Okay, this means that if I double my distance from my point source, the intensity will be 1/4 as much.
Never
Yes?
mind if I can answer that question.
Okay. Okay. If I double my distance, the intensity will be 1/4 as much. If I triple the distance, the intensity should be 1/9 as much, etc. Now consider as one example, just being in this room. We have the camera and Espen, who's right here at the front. We have Joseph at the back, not way back, but farther back. The distance from me to the camera is, just eyeballing it, about 1/3 of the distance from me to Joseph. This means that the camera is picking me up, at least nominally, 9 times more intense than Joseph is. Now, does this mean that it's getting 9 times more power from my voice, anything like that? Not necessarily. Your detectors are different sizes. The microphone is a different size. It has a different efficiency than your eardrums. Here's an interesting thing that you can do with this, by the way. Everybody go ahead and close your eyes for a minute. I'm going to walk around the room, and in a minute I'm going to snap. I want you guys to point to where I am when I snap. Go ahead and close your eyes. No cheating. Can't look. Your eyes are open. All right, go ahead and open your eyes. See how you did. Well, so you did pretty well. A lot of the fingers are pointing like in this general vicinity. So you can actually kind of hear where a person's at because you have 2 detectors. Most of you do anyway. If you're deaf in one ear, then this may not work so well. But you have 2 detectors. There's 2 things that these 2 detectors are able to do. One is, because the distance is slightly different, there's a slight difference in the amount of time it takes for the wave to get to one ear and to the other. The other is, because you have slight differences, and this is the one that's more important here, because the time of flight's usually pretty minor, and your ear's not necessarily tuned to that. The other thing, though, is that the intensity is different. Because your ears have slight different distances, the value of this, and therefore these 2 is different. You can get a rough location of it because your brain can process that this ear heard it slightly less loudly than this one, and so the difference must be so much. So you can guess based on that. Okay, so where does the decibel scale come into all this? Well, I already said that there's a factor of 9 difference, roughly, between the camera and Joseph. And if we go diagonally across the room like this, it may be more like 5 or 6 times greater distance. Say 5 times greater distance. We have a factor of 25 there. And now consider that you have many differences in how loud the source itself is. I'm not an especially loud source, as many of you have complained in the past. But others could be more of a loud source. So in order to keep track of the fact that we have such a wide number of possible intensities, we use the decibel scale. The decibel scale is logarithmic. We usually write decibels as an intensity level. We use a beta for that. And it turns out that the way that you figure out beta is you take 10, you multiply it by the log, base 10, of your intensity, the actual sound or source intensity at wherever you're measuring it. And then you divide this by some known base intensity, I naught. So what is the value of I naught, the known base intensity? It turns out that I naught is 10 to the minus 12 watts per meter squared. squared. Okay, this logarithm multiplied by 10 basically tells you that each time you increase by 10 decibels, you've actually increased the intensity of the sound by a factor of 10. So 0 decibels does not mean no sound. It just means this much sound, this much intensity. 10 decibels is 10 times this. It will be 10 to the minus 11. 20, you have 10 to the minus 10, and so on. If you increase by 3 decibels, for what it's worth, you've roughly doubled, not exactly, but very roughly doubled the intensity. Okay, so 23 decibels is actually twice as intense as 20 decibels. So we're out of time for today.